Hello everyone, I am Orko and in this video I am going to show you how to make counter circuits. We know counters are of two types. One is synchronous counter and another one is the asynchronous counter. The synchronous counters are the one in which an external circuit is used to produce a pulse that is synchronized with the internal clocks. But in case of an asynchronous counter, the external circuit is used to directly set or reset a flip-flop. In synchronous counters, if you look carefully at the when I will make the circuit, that all the flip-flops are clocked by an external clock pulse. But in case of asynchronous counter, only the first flip-flop is clocked externally and that becomes our LSB, and all other flip-flops are clocked by the output of their respective last flip-flop. Now this thing you will understand more clearly when you will see my video on asynchronous counter. Now the thing is how to draw the circuit diagram of synchronous counter. Now the first thing you have to do is to draw all the stages. Now here I have made a synchronous counter of mod 4. Now for mod 4 we need 4 distinct stages I have made, and it is a mod 4 ring counter. And this method is applicable to draw every kinds of counter like ring counter or even not a ring counter. This means that the count will end at 3, that is the fourth stage, and it will not go back to the 1. That this is a synchronous ring counter since it's since after the last stage, that is the stage number 3, it goes back to 0. So this is our mod 4 synchronous ring counter. The first thing we have to do is to draw all the stages. That is, we have to draw all the stages we need to be displayed. That is, we have to need 0. At first of all we need 0, so 0 0 0. Then we need 1, so 0 0 1. We have to write it in binary. Then we need 2, then 0 1 0. Then number 3, then that is 0 1 1, and then we again go back to 0 because I have got here 4 distinct stages. So it is our mod 4 counter. Now the second thing we have to do is to note all the changing states and determine the total number of flip-flops required. We know that each flip-flop gives one bit of data, that is the data, and another one is the complemented data. Here you can see that if you look carefully at these stages, the first bit, that is the MSB, is always 0 at every case, but the last 2 bits are changing. For example, it is 0 at first 2 cases and then it is 1 for the last 2 cases, and similar is the LSB 0 1 0 1, like this it is going on. This means that our last 2 stages are changing. That's why we need 2 bits of data to display our counter. That means since each flip-flop gives 1 bit of data and we need 2 bits of data to be displayed, we need 2 flip-flops. Now these flip-flops can be JK flip-flop, T flip-flop or D flip-flop. I prefer T flip-flop or D flip-flops because I have to draw less number of K-maps than JK flip-flop. Because in case of JK flip-flop, I have to draw the K-maps of J's and the K-maps of K's. But in case of a T flip-flop or D flip-flop, I have to draw only the K-maps of T and D. So this is one of the advantage of using T flip-flop or D flip-flop only in case of synchronous counter. In case of asynchronous counter, we can make the circuit only with the help of JK flip-flop. Now, one disadvantage of using T or D flip-flop in case of synchronous counter is since at JK flip-flop there was 2 terminal J and K, but in case of T or D we are getting only 1 terminal. So at this time my circuit may get more complex. So this is one of the drawbacks of using T or D flip-flop. Now after this stage we have to go to stage 3. Now this stage 3 is the most important part of drawing the circuit diagram of mod N synchronous counter. Now first of all we have to draw 3 tables. One is the possible combinations table, then it is the next table, then it is the excitation table. Now in case of possible combination table we have to make 2 columns. Now these 2 columns will be of the 2 bits. The bits we have to write in descending order. For example, if we required 3 bits, for example, if it was greater than mod 4, for example, if it is what mod 5, then we have to count it up to 4, and at that time this MSB, that is this first bit, will become 1 in case of the 4th stage, since that was mod 5 counter. In that case we require 3 flip-flop and we have to make 3 columns. the first column will be of Q2, then of Q1, then of Q0. So that was in case of mod 5 counter, but since we have designed mod 4 counter here, so we don't need the any third flip-flop. We have to we can make it by using both the two flip-flops, that is D0 flip-flop and the D1 flip-flop. Okay, now so first of all I have to draw the table of possible combination. Now this possible combination means the 2-bit, we have to write it in descending order, Q1 and Q0. We have to write all the possible combination that may occur in case of a 2-bit data. This means that in case of 2 bits we can write it 00, it may become 00, it may become 01, and it may become 10, then it become 11. If it was if I have to write if we need 3 flip-flops, then we have to write then Q2, Q1, Q0. At that time the possible combination then would become 000, then 001, then 010, then 011, then again 100, then 101, then 110, then 111, in this way. Now my next column or the next set, I can say, is our next state. This means by looking at my possible combinations table, I have to write the next state table. Now if we also refer to our stage diagram, we can see that when it is 0, after that it will become 1, then 2, then 3. We have to write the binary values here. When I have got 00, after that I need 01, that is after the next pulse. After this next pulse, when after that is 01, we need 10. After 10 we need 11, and after 11 I need 00, since I am designing a mod 4 ring counter. In this way I have to make the next state table. Now if it was not a ring counter, then at that time I don't need anything after 3. At that time my next state after 3, that is 11, would then become don't care, don't care. We have to make the zeros with don't care symbols. So after completing this table, I have to write the excitation table of both the flip-flops. Now you know very clearly what is the excitation table of D flip-flop. You can refer to the excitation table of D flip-flop, and at that time you have to consider Q1, that is small q1 and capital Q1, by looking at the two values, taking this is as Qn state and this state as Qn plus 1 state, because obviously that is thing we have to consider this table as the Qn state, and this table is the next state, that is it should be Qn plus 1 state. So if Qn is 0 and Qn plus 1 is 0, then according to our excitation table our D will be 0. In this way I have to make the table for both D1 and D0. Now our fourth state is draw the K-maps of D1 and D0 taking the values of Q1 and Q0. This means I have to draw the K-maps of D1 and D0 in terms of Q1 and Q0. That means if you draw the K-map, then our vertical side will become Q1 and our horizontal side will become Q0. But I don't draw K-maps here because this truth table is a very simple truth table, and I can write my Boolean expression by looking at the truth table. It is very easy, but when it will become more complex, then you need to draw the K-maps. Now if you look at these two tables and this table carefully, you will find it is 0 0 0 0 0 1, then 0, then 1 0 1, then 1 1 0. This means the D1 we are getting is the truth table of XOR gate. This means D is equals to Q1 XOR Q0. So I have directly written here Q1 XOR Q0. And if you carefully look at the D0 table, it is just the inverse of this table. That is 0 0 we are getting 1, 0 1 0, then 1 0 is 1, then 1 1 is 0. But if you look carefully, it is just the complement of this Q0 part. So I have just here written Q0 complement. Now once you get the Boolean expression of D0 and D1, then we should not wait, and directly we should move on how to draw the circuit. Now first of all I need to draw two flip-flops of D, that is D flip-flop, and all the clock connections has to be made, all the clear connection has to be made at high, and all the preset has to be made at high. Now this is the first thing you should do while drawing a synchronous counter or a synchronous ring counter, any type of synchronous counter. Now as you can see, all the connection I have made using my blue pen, and as I have told while telling the difference between synchronous and asynchronous counter, that in case of synchronous counter an external circuit is required that is synchronized with the clock pulse, and that external circuit I have drawn here using my black pen. You can see it is completely an external circuit which I have connected with my two flip-flops, and it is not connected to the preset or clock or the clear portion. So how I get the circuit? Now this circuit I have get from the K-map expressions, that is D1 is Q1 XOR Q0. So I have taken Q0 and Q1, and I have connected D1 with the XOR gate and the D0 with the Q0 bar. We have to make the circuit connection like this. After we have made the circuit connection, we should move on to perform the experiment practically. Now in the practical experiment, I have used an IC that is quad D flip-flop. It is 74LS175. It is a quad D flip-flop, and this IC is very useful for making synchronous counters, because in case of synchronous counter I need all preset, clear and clock to be connected at a time, and in this IC these threes are connected to a single pin. The clock is connected to pin 9, the preset is inbuilt high, and the clear is connected at pin number 1. So this IC becomes very useful for drawing the flip-flops of even mod 16 counter, but it should be an synchronous counter. In case of asynchronous counter, you can draw the circuit diagrams, and also you can make the circuit practically only by the help of JK flip-flop. So now let's move on to perform the experiment practically. So I have made the circuit on the breadboard, and here is my clock enable switch to enable my clock pulse. Okay, so now I will be providing the clock pulse, and let's see the result. First of all, I will be giving the clock pulse from my Arduino. So for this I need to connect the power to the Arduino first of all. Okay, I have connected the power and the clock connection of Arduino, and now I will be giving the power to the circuit. Okay, so now let's wait for some time to settle all the flip-flops and the clock. Now you can see my clock is now perfectly working, and now my clock is now perfectly working. Okay, and now I am going to switch my output to the display, and now I will be enabling my clock pulse. So now if you carefully look at the display, you will find it is counting. One is counting up and another one is counting down. Okay, so this is the circuit diagram I have made on the breadboard of a mod 3 synchronous counter. You can draw also more difficult circuits, that is, and you can make circuits up to mod 10 synchronous counters also. So this was my video on synchronous counter, and I have also uploaded a video on asynchronous counters. You can check that video also. You can check my also video because I have provided the link at the end of the video. So that's all for today, and obviously and please subscribe my YouTube channel for more videos, because I will be uploading more videos on electronics tutorial. So thanks for watching, and see you in the next one.